Let's now return to our 40-meter string, where we determined that the velocity of the pulse was 77 meters per second. We want the frequency of the second harmonic. The second harmonic is the one where the two ends of the string go like this. Okay, the second harmonic has wavelength lambda equal to 40 meters. That is, we see that when the string's in this configuration, we've got an entire wavelength matching the length of the string. So if lambda is 40 meters, then what's our frequency? Well, the wave will move 77 meters in a second. The wavelength is only 40 meters, so we're going to get almost 2 complete waves moving by us in a second. Every time a wave moves by us, this thing goes through a complete cycle. Our frequency is therefore 77 meters per second over 40 meters, or 1.93 cycles per second. My units weren't right there. That should be per second. Okay? The third harmonic is the one where these two ends are moving together while the middle is moving opposite to either of the ends. We can see that the third harmonic occurs when 1.5 complete waves fit into the 40-meter length of the string, so that the wavelength is 2/3 of the string length, 2/3 of 40 meters being 26.7 meters, so that the frequency is 77 meters per second divided by 26.7 meters, or 2.9 seconds. Again, we can visualize a second's worth, almost twice the length of this string, and one cycle being only this long now, almost 3 of those cycles will pass us in a second. So this thing will go through almost 3 of its complete cycles in a second. If we match the harmonics of the string to the frequencies, the first harmonic, or the fundamental, we found had a frequency of 0.97 seconds. We call that F0. The second, 1.93. The third, 2.9. We see that these two frequencies are simply multiples, integer multiples of the fundamental frequency. This one being twice the fundamental, this one being 3 times the fundamental. When Josh did his experiment with the beeping timer, the program Harmonic timer, remember he did the experiment that you are going to do or have done, where we stretch the string out and tension it with a couple of rubber bands after braiding the string together to make it heavy and also to make it fit within a reasonable sized room. He observed the first harmonic taking place with a period of 0.89 seconds, the second with a period of 0.44, and the third with a period of 0.33 seconds. Now again, what he did was he was just wiggling the string back and forth at the end, and he observed the period of the harmonic timer, which made him go faster and faster. He looked up when he found that the string was resonating in one of these harmonics, and found a period of 0.89 seconds for the first, 0.44 seconds for the second, 0.33 seconds for the third. The corresponding frequencies, remember the period is a number of seconds, the frequency is a number of cycles per second, and it's going to be the reciprocal of the period. The frequencies were 1.12, 2.27, and 3.03 cycles per second, which are pretty much in the right ratio. This is about twice this. This is about 3 times this. It's actually a little less than 3 times, but it's a little hard to observe exactly where these things occur. This is fairly good confirmation, again within 10% or so, that the frequencies are in that 1 to 2 to 3 ratio. To calculate the velocity of Josh's wave, we noticed that the string length was 15.5 feet. Now we did this in the classroom, where the tiles in the classroom are almost precisely 1 foot square, And we counted tiles to determine this rather than using a meter stick, and this is why we're in British units, feet. The frequency of the fundamental was, as we said, 1.12 hertz. So what's the velocity of the fundamental? Well, we have 1.12 cycles per second. Excuse me. The complete cycle of the wave is going to be twice the length of the string, or about 31 feet. So the wave will be traveling 31 feet for every cycle, and 1.12 cycles every second. That means the wave is going to travel 31 feet 1.12 times every second, or the distance in a second is 1.2 times 31 feet, or 34 feet. So the velocity is 34 feet per second. We could similarly find the velocities of the other harmonics. The velocities are going to be the same, pretty much. The second harmonic will have double the frequency of the first, but of course it has only half the wavelength, so it travels the same distance. The third harmonic will have about triple the frequency of the first, but it travels only a third. The wavelength is only a third as long, so again, it has the same velocity.